In the last lecture, we introduced the concept of determinant, which is a number that summarizes somehow the entries, the properties of a matrix, in particular of a square matrix. So the determinant of a square matrix of size 2 is particularly simple to compute. We saw it in class in the last lecture, and it's simply the product of the entries on the diagonal minus the product of the entries in sort of the reverse or opposite diagonal. So this is very simple to compute. And then we notice that, well, if I have on the other end a matrix of size 3, it becomes challenging. It looks messy, the expression of the determinant, and we discussed that there is one way we can do it in terms of cofactors. So what I want to do next is to actually formalize this concept. And so let's look at the formula. I have a matrix A, and its determinant is going to be equal to an expansion in terms of a row or a column where I multiply the elements of that row or column that I chose by what is called a cofactor. So in order to compute the determinant, I need to pick any row or any column of my matrix and then multiply the entries of either the column or the row that I picked by what is called a cofactor. And a cofactor, it's basically the determinant of a submatrix where a row and a column are deleted. And then we multiply by that determinant by either a -1 or a +1, depending on basically this number here, which is the sum of the row index and the column index. So let's go back just for a second. So here I have this matrix A, and I decided to expand over the first row. Okay, so what I have is the entries A11, A12, A13, which are in the first row, multiplied by the determinant of the submatrix where I delete, in this case, the first row and the first column. So I have A22, A23, A32, A33. A12 is multiplied by the determinant of the matrix where I deleted the first row and the second column. So I have A21, A23, A31, A33, and so on. Furthermore, I also have to multiply this determinant by -1 to the power I plus j, where I is the row index and j is the column index. So if I pick the first row and the first column, 1 plus 1 is equal to 2, and so I have a plus. Here I deleted the first and the second column, the first row and the second column, and therefore I have 1 plus 2, which is equal to 3, which is an odd number, and therefore -1 to the power of 3 is -1, and this is why I have this minus here. So in your interactive tutorial, you have an example, an extended example, where we review all these steps, and furthermore also some additional exercises. One more thing that I want to mention about determinants are some properties. So, and in particular here I want to highlight 3 which are particularly useful. So if I have a row or a column of a matrix which is full of zeros, then the determinant is 0. So it is quite easy to compute if I notice that a row or a column are just a vector of zeros. A second property which is useful in practice, it's very useful, is that the determinant of a product is equal to the product of the determinants. So one thing that we will see at the end of this class is that I can often write a matrix as a product of matrices. So if for that product of matrices, computing the determinant of each individual matrix is very easy, then computing the determinant of the original matrix is easy too. And the last property, which also comes into play often, is that if I have a diagonal, or more general, a lower triangular or an upper triangular matrix, then its determinant is simply the product of its diagonal entries. So if I have a matrix which is triangular, its determinant is just the product of the entries on the diagonal. So it is very fast to compute. And again, in the interactive tutorial, you have an exercise which shows you how to take advantage of this property.